And on the bench, I thought I would take a look at projects that I'm actively working on, so stuff that's not yet complete. What I've been doing recently is working on my thrust test stand. My current stand is based around an HX711 and a Teensy 3.2. Recently, the Teensy 3.6 came out, which has a much faster processor and, more importantly, an SD card slot that's hooked up via SDIO, which should be much faster than the SPI-based connection that I'm currently using. So when I saw this, I thought it would be a good time to kind of clean up my current thrust stand and do a new board that will hopefully have less noise and better filtering for the signals. And I'm going to do it based on the Teensy 3.6. The Teensy is really nice, in particular for this project, because it has actually two ADCs. So I can sample, say, the voltage and the amperage at the same time and get not only twice as many data points in the same amount of time, but I can also keep measurements in sync with each other, so I'm not sampling the current after at a time sample after the voltage, and just to try and reduce kind of drift or lag in multiple things. The other big change that I wanted to do with this is include a Huzzah Wi-Fi module, so I can control it. Like right now, I just have it all reading config files off the SD card and triggering off a physical button. But I'm working on the thrust or the lap timer project. I've really liked working with these Wi-Fi modules and controlling stuff on a tablet or a cell phone through a web interface. So I definitely want to do that here to be able to trigger the stand. I don't have to be standing right next to it, and be able to get a peek at the data right away without having to go back to my computer to read the logs. So that's really kind of the big usability feature that I wanted on there. Also, switching from, I'm currently using a TMP37 standalone kind of dedicated temperature sensor, but it's really slow to react, and it's a TO92 package, so it's also kind of hard to get into, to squeeze into a small motor and get it contacting the windies directly, which I think would be really nice to be able to have. So I'm building the new one with the idea that I'm going to use little thermistors, the same type you'd use for a 3D printer. Rather than just reading them like a voltage divider, I've got a pair of fixed current sources, which should keep the self-heating on the thermistors incredibly low, and then just reading those directly through a little bit of a filter to get rid of the noise. So those should have the thermistors that I was looking at. As long as I keep the B value under about 3.5K, I don't need to reduce it'll be able to be read through just a 3-volt ADC range that I'm planning on having for the thing without having to reduce it any. So that part is really simple, and they should have a time value of like 6 seconds versus 22, I think, for the TMP37, so they should be much more reactive to changes, which would be really nice to be able to start recording temperature again, and to have 4 of them, so I can have one on the motor and one on the ESC, and then have 2 others, maybe a motor casing and motor winding or something like that. I am also still keeping the TMP37 around because to use as a global reference, that is going to be a lot better calibration. It's calibrated from the factory, so I can use that to refer against the calibration for the thermistors independently, and just can have that built in as a baseline. I also thought that rather than using the HX711 board from SparkFun, that I would just integrate the whole thing onto my main board, and so I have the factory recommended kind of set up for that, along with the inductor that SparkFun put in there to reduce a bit of noise. I'm also going to try, I'm not sure if it will work, the crystal pins on the load cell amp does support up to 20 megahertz, which would give a higher, almost double the sample rate, which would be nice. I'm already kind of sampling as quickly as possible and then trying to reduce noise in software by averaging rather than letting it hardware average. But I'm not entirely sure if the crystal resonator or the crystal setup is going to work. It's not very well documented. The datasheet only says just to put a crystal directly across it, but I've seen some posts from people saying that they've tried that and it doesn't work. So I'm going to at least populate the footprint for it. I can try it with and without capacitors, and then if nothing else, just have a little ground pad that I can short the XI to ground, and then it'll switch automatically back to its internal clock. So and then I'll just have the empty footprint and can live with the lower data rate. The other thing that I wanted to try to do this time around is do more signal conditioning. I had struggled using these Avago or Allegro Hall effect current sensors. I have 100 and 200 amp bidirectional current sensors that I wanted to use instead of the autopilot ones. But I found that on my current setup they were really noisy. They're 5 volts, 5-volt sensors, and I'm trying to read them on a 3-volt ADC. So I've got to drop them down, and had problems with the load resistor that it wants, and trying to do the resistor divider to get the value down. So I'm going to throw them all behind an op amp so that I can buffer it, and then just have a straight divider, and have one both for the autopilot current sensor, which is a 3.3 volt sensor, and then one set up with the load resistor and filter that are called out on the Hall effect sensor data sheet, along with dropping that from 5 to 3 volts. So 3.3 to 3 for the autopilot, and then 5 volt to 3 for the other. And I'll have both of them that I can use interchangeably, and then I'll just switch that in software. I'm using the 3 volt specifically because I want to throw a 3 volt precision current voltage reference, a shunt reference across the AREF. So I'm switching it over. Unfortunately, my current one, I used a switching regulator, which was really not a good idea since I want it to be low noise. But I'm going with a dual linear regulator on this, trying to get the power source to be as smooth and clean as possible, and then going the 3 volt shunt reference, just to have that little bit of headroom. I mean, because you don't want to have a shunt reference at the same voltage that your main voltage is, because it can't go over if the system voltage is a little low. So we need to have a bit of a drop there just to make that. And so my analog reference is going to be 3 volts. So I've got to drop everything down to that point where normally I would be able to read a 3.3 directly. So I was going to do that. Haven't worked this part out yet. The optical tack is working really well as it is now. The one main thing that I still need to look at is I want to put a digipot on there to do self-calibration or setting levels so it can read. So I need to look up what values I actually used on my current one, because that's been working okay, but I really want to be able to control that from software. And then the probably most complicated thing that I'm trying here as well is in the voltage reading side of things. I really want to be able to read anywhere from 3 volts or a 3-cell up to 6-cell, but I don't want to just set the system to 6-cell because I'm going to lose a lot of resolution on the ADC. So I thought I would try an auto-ranging system. So this is the main voltage divider for the VBAT, the main battery voltage, with just a simple RC filter to cut it off at just over 1 kilohertz. I might go up a little higher on that depending on what the sample rate that it seems. Currently I'm getting about a 1 kilohertz sample rate. I'm hoping to increase that a lot, so I might have to change all the filter values later. But the main idea is my normal divider is set for 6S, and then I have a P-channel MOSFET in line with a second resistor, and then run 2 resistors in parallel to drop that divider value down for range specifically for 5S, 4S, and 3S. So I can toggle those on from the MCU. It defaults on power up to the highest voltage range, and then can sense if it can drop itself down and gain back more resolution. The other thing that I wanted to be able to do is, again, self-calibrate that, and so I've got another set of MOSFETs at the top, one that switches the main battery voltage to feed this main divider, and then also will let me turn that off and switch on just the feed from the 3.3 volt regulator that the main MCU runs at, with a diode to keep the high voltage battery from feeding back into the 3-volt rail, so that I don't have to worry about calibrating these divider values externally. I can just feed 3 volts, which I know is going to be, about 3.3 volts minus the dropout of the diode, and then switch between all of these values, and then I know that I'm feeding it the same voltage each time, and so I can calibrate each of these divider settings so that they all read the same compared to each other, and then I can just have one main voltage calibration for the whole thing, and then once I calibrate this 6S divider, then I can match all of the other voltage ranges to that calibration internally, automatically in software, and it can control that, whether we're feed it calibration voltage or feed it the battery sense, and that there's no worry about damaging, because it's only a 3-volt calibration voltage. Even if I feed it down to the lowest, I can turn, you can even get slightly lower than 3S range by turning on all of the ones in parallel with each other, and I don't have to worry about damaging the ADC. So that's about where I am. I'm still filling out packages on things and starting to fill in some final values and stuff. Still need to do the optical tack, but I feel like I've got all this stuff in there, and really hoping to tie this up and send the board out to get it printed, because I would really like to be doing more benchmarking stuff again, and the extra software capabilities that this will give me will be really nice to have, especially if I can get a much cleaner, less noise in the voltage and amp readings.